Once the risk table has been used to determine severity, safety standards usually convert that risk to a SIL to determine the level of engineering rigor that should be applied. A SIL is a safety integrity level. SILs are generally divided up into a handful of bins, where usually the highest risk is called SIL 4, which is considered catastrophic. In many systems, this corresponds to a large fatal event, such as a severe train crash involving multiple fatalities that could result from a software defect. Lower SILs correspond to lower levels of risk that might, for example, involve only injuries. The idea is that the higher the SIL, the more engineering rigor needs to be applied. As an example, let's consider IEC 61508, which is a software safety standard used in the chemical process industry. That standard uses SIL 1 as low risk and SIL 4 as a very high risk. It then shows how to mitigate risk by applying engineering rigor. A small subset of the techniques required by the standard are shown in this table. You can see many different software techniques in the rows, with 4 columns corresponding to the 4 SILs used by the standard, SIL 1 through SIL 4 highlighted in yellow. For SIL 1, you can see that some techniques are recommended, which means they are nice to do but not strictly required. One technique using structured methods is highly recommended, which as a practical matter means you have to do it for safety even at SIL 1. At SIL 2, some more techniques are recommended, and dynamic techniques are not recommended, which means you should not use them. That's because if the system changes during runtime, the system that's running isn't the same one that was tested, so it's hard to know how it will behave. At SIL 3, which is considered life-critical, 4 more techniques become highly recommended. At SIL 4, even more techniques are highly recommended, causing the application of even more engineering rigor. There are many pages of tables like this in this standard, but the general idea is that safety standards enumerate techniques to ensure that high SIL software is essentially free of mission-critical defects. The higher the SIL, the more engineering effort must be applied to make sure that nothing slips through into a deployed system.